Good afternoon.
Hello guys, nice to see you. Maybe let's wait a few minutes. Maybe more people will join. Okay, last time we discussed electric power, so we have shown how electric power, which is dissipating at electric resistor, depends on current which flows through this electric resistance. We have shown that there is quadratic dependence, so it's power proportional to current in second power. And that is the main feature which should be taken into account, that particularly the electric current defines how much power will be dissipated, and that already has to be considered for developing the design of different electric devices, even resistors, because as you may know, resistor, there are different types of resistors, and they vary by resistance, which can be quite in a broad range from like tenths of ohm to like giga ohms resistors, and also by power. So there could be a resistor with the same resistance, like 100 ohm, for instance, but one will be so tiny that you can barely see it. Another could be really huge and weight like kilograms. So it all depends how much electric power will be dissipated on this resistor. And of course, that is strongly dependent on electric current, which is going to be running through it, this resistor. So now we are proceeding further with the analysis of DC electric circuits. And one of the key element of any direct current circuit is battery. Obviously, we need some driving force which will cause this transport of electric charges in the circle, like in the electric circuit. And definitely this is indispensable component of any electrical circuit. So today we will start from this, and we will consider a combination of resistors, like series and parallel connection of resistors. And at the end of the lesson, we will discuss Kirchhoff's rules. So those rules which help us in more general case to analyze electric circuits when it's more complex DC electric circuits, when they are a bit more complicated than just single battery and a certain combination of resistors connected in series and in parallel. So when electric circuits are a bit more complicated, then Kirchhoff's rules can help us to solve, to set some linear system of equations, which will provide us with necessary like unknown information, like by solving which we will get unknown information about electric current in different parts of electric circuit, and also potential difference between different points of the electric circuit. Okay, so let's me change the camera. And let us proceed with this battery. So one of the key characteristic of electrical battery is so-called electromotive force. In short, there's like abbreviation, it's called EMF, electromotive force. And this is the maximum potential difference which can be achieved at the terminals of the battery. So real batteries, it should be taken into account, are made of some matter, some material, and obviously this material possesses some certain resistance to charge transport. So these electric charges are losing energy while moving through this material. And of course, it is like all good batteries are designed in that way, that this so-called internal resistance is minimum, because we don't want to lose energy on internal resistance. However, real batteries always possess certain internal resistance. And that's why usually we show such a system of a battery which generates this electromotive force, and in series connected resistor R. So this is, we can mark electromotive force as capital epsilon, plus minus, and then we put it in such dashed box. So this dashed box shows us that this is actually a single device. It's our battery, but we should consider some components of this battery, so like some voltage, like potential difference generator, and in series we have some like series resistance, internal resistance of this battery. So this should be taken into account because it actually will define what current will flow in our electric circuit, and also what potential will be at the terminals of our battery. So if we consider, for instance, at the beginning, some ideal battery with internal resistance equal to 0 ohm, then the potential difference between terminals of this battery will be equal to its electromotive force, like always, because we don't have any internal resistance. However, this is only ideal case. In real case, usually this resistance is not equal to 0, and that's why the potential difference between terminals of battery will be always smaller than epsilon if electric current is not equal to 0. Because if electric current is equal to 0, we have so-called open circuit condition. And in that case, there is no voltage drop over this series resistance because current voltage drop over the series internal resistance of this battery will be product of current times, current times internal resistance. Since current is equal to 0, then this product is also equal to 0. And in this particular case, potential difference at the terminals of the battery will be equal to its electromotive force. However, it was only under open circuit condition, and that is not a working condition because voltage is high. Let's say it's equal to electromotive force, EMF, but current is 0. So it means that there is no power delivered to the external circuit, electric circuit, and this battery doesn't perform any work. So this is some extreme condition, which is not working condition, just some so-called open circuit condition. There is another, just an example, is another extreme condition, which is short circuit condition, that when there is no load resistance, like load resistance is equal to 0. And one terminal is just directly connected to the another terminal of the battery. So that condition is called short circuit condition, and it's also some emergency conditions for electric circuits. Of course, we want to avoid them because we will get a lot of current, which actually does no useful work, only burns, like damages power sources and electric wires. So now we will consider an example of a very simple electrical circuit. So here is our battery with internal resistance R. So here plus minus, we have some epsilon, electromotive force. And then we show this dashed structure. So this is our battery. Then we have some load resistor. Will be capital R. We don't consider any potential drop over connectors, like these wires are considered to be to possess 0 resistance. So here we have some current running through this circuit. And what we want to do now, we want to consider how potential will vary from point to point. So we will have some points of our interest. This will be point A, B. Here will be point C. Here D. Here point E, and here point F. Okay, now let us make one plot. So here we have our potential difference, and let us represent in one line this electric circuit. So it will be our battery, internal resistor, and our resistor. So we have all these points now in one line. A, B, C, D, E, F, and can consider what is going on with the electric potential at each of these segments between points. So here, if we start from point A, it actually can be considered as potential 0. Then we increase potential because we have this electromotive force. We increase potential. Maybe we can use some okay. We increase this potential here very rapidly because charges move through the battery, and this battery increases the electric potential. And then it saturates at some level, so we don't have any voltage drop over electrical connectors. And then we have this internal resistor, which is R, and here is our load resistor. So when electric charge moves, like electric current flows through this internal resistance, we lose certain potential, which again then is saturated. And here, this saturation level happens at this epsilon value, electromotive force. Then the second saturation is the product of electric current which flows through this circuit times load resistance. And then in between points E and F at load resistance, we drop our potential to 0. So we come back, make a circle, and come back again to point A, which is in front of our battery with 0 potential. So we go from 0 potential to back to 0 potential. And this difference here between electromotive force and voltage drop over load resistor is current times internal resistance. So obviously we want to make our batteries with as small internal resistance as possible, because we don't want to have this voltage drop, which is not useful, just warms up our battery and causes loss of electric energy, and also causes some potential damages and overheating of our battery. So now we can write the following, that potential difference at the terminals of our battery will be equal to the electromotive force of this battery. And this, by the way, coming a little bit back, this electromotive force is defined by the materials and design of the device engineering of this battery, and also materials which are used in this battery. So it's a feature of the device engineering and material science of this battery, which then we need to subtract here current times R, internal resistance. So of course, internal resistance is also a parameter which defined by materials used in the battery and the way how this battery is designed. So everything should be made in that way that we have as small resistor internal resistance as possible. So this is the value for voltage at the potential difference at the terminals of some real battery. And of course, in our electric circuit, which we considered, this will be equal to the product of electric current to the resistance, like our load resistor. So in other form, we can write that electromotive force is equal to I times R plus I times internal resistance. And from here, we can express so-called Ohm's law for a direct current electric circuit, which is electric current I is equal to epsilon electromotive force divided by the sum of load resistor and internal resistor. So this equation, please remember, this will be used for solving different problems. And keep in mind that you always need to take into account, besides the load resistor, also internal resistance of the electric battery, only if it is stated in the problem that we have some ideal electric battery with internal resistance equal to 0. Okay, now let us consider the electric power. So for this purpose, we can multiply this equation by current, by E. So like I, so it will be epsilon times I equals I square times load resistance plus I square times internal resistance. And we see that the power which is delivered by the battery by converting internal chemical energy into electrical energy is divided now in two components. So one component is useful component, that one which performs some work, and another component which is not useful and only causes some technical problems and losses of electric energy. Obviously, we want to avoid this second component. Now, let us consider what will be the maximum power, electric power, which can be delivered to the external useful load resistor by some battery with some internal resistance R. So for this purpose, let's consider that we have electric power equal to I square I square times R. So we are interested in the useful power which can be delivered from the battery. And this electric current, we know the expression for this. It's epsilon divided by the sum of load and internal resistance. So that's why it will be epsilon squared divided by R plus R square times R. Okay, so now we want to know at which resistance, so which load resistor we need to pick up and connect to the battery in order to get some maximum value of the um, electric power dissipated on this load resistor. So for this purpose, we need to take derivative of this function, because here we have a function of this power P of R over R and set it to 0. So this is the condition for finding the maximum of a function. And that will help us to determine at which R we will get maximum power. Let's go to another slide so we have enough space. Let's write again this equation. So it's like this one. We can see it will be P equal to epsilon squared divided by R plus R squared times R. And now we take the derivative. It's dP over dR will be equal to d over dr. Here will be, we can restruct a little bit, rearrange this equation. Let us write like this. It will be epsilon squared times R times R plus R in the power of -2. Okay, so now we need to take the derivative, and actually what do we have here? Here are here's this function when we consider P as a function of R. So here we have a product of two functions. We have R and we have R plus internal resistance in the power of -2. So that's why we need to apply this rule for the derivative of a product of two functions. And in this case, we will get, first we will differentiate this R. So it will be just epsilon square times R plus R in the power of -2. And then we need to add derivative when we derive over this function. So it will be epsilon square times R times -2 times R plus R in the power of -3. And then derivative of expression in the parentheses will be just unity. So because our internal resistance considered here as a constant. We don't vary it. And finally, we can set everything to 0, as we mentioned at the beginning, in order to find this condition when R is going to be when we get some specific value of the load resistor, which provides conditions for the maximum output power from this battery. So in order to proceed further, let us multiply and divide, like first equate like first term by R plus like load resistor plus internal resistor. So let us write it here. We can write epsilon square divided by R plus R square. Then we multiply and divide by R plus R. And we do this in order to have in our denominator also power of 3. So we have the same denominators. Minus 2 epsilon. So we take into account this minus. So that's why here we have minus 2 epsilon square times R divided by R plus R in the power of 3. And this we can write as follows. So we can factor out epsilon square. Here will be R plus R in the power of 3. Then we have R plus R and minus 2 R, capital R, this load resistors. So finally, we get epsilon square R minus internal resistor minus load resistor divided by R plus R in the power of 3. And this we set to 0. So from here, we see that this will be equal to 0 only when, so we don't assume that electromotive force is equal to 0, obviously. So we have some working battery, not broken. That then it is possible only in case when internal resistance is equal to load resistance. So this is the condition for the maximum power which is delivered by battery to the load resistor, I square maximum R. So in order to get maximum power, useful power from the battery, it's necessary that load resistor is matched, like equal to the internal resistance of the battery. So this condition we define. And now let us go for considering the different connections of resistors, which could be met in different DC electric circuits. So first, we will start from the series connection of resistors. And for this purpose, we consider such electric circuit. Resistor 1, resistor 2, have some voltage drop, or potential difference 1, potential difference 2, and some battery. With some electric current, assuming that internal resistance of battery in this case is equal to 0. We don't take this into account. So since this resistors are connected in series, that automatically means that the amount, like electric current which flows through these resistors, will be the same. So what is electric current? Is a certain electric charge which passes the resistor, or a cross section of this resistor, per unit time. And if per unit time we had some electric charge passed through resistor R1, there is no other way than the same amount of electric charge will pass during the same time interval resistor R2. That's why their like electric current through these resistors will be equal, and it will be I1 equals to I2 equals to I, the current in the circuit. At the same time, this potential difference, which is generated by the battery, will be split in two components because we have two resistors connected in series. So we have total potential difference will be equal to delta V1 plus delta V2. So now the question is it possible to substitute these two resistors with one resistor, so-called equivalent resistor? It is possible, and in order to figure out how to calculate this equivalent resistor, we need to recall that this voltage drop delta V1, it will be equal to I times R1, and delta V2 is equal to I times R2. So now we can write that total potential drop, which is the same in both electric circuits. In the electric circuit at the right side, it will be equal to electric current I times R equivalent. And from electric circuit in the left, it will be I times R1 plus I times R2. So since electric currents are the same, we can cancel them out, and from here we get the expression how we calculate equivalent resistance of two resistors connected in series. It will be R1 plus R2. So when we connect resistors in series, we have to add the electrical resistance in order to get some equivalent resistor, like single resistor, which represents the same resistance as a battery of resistors connected in series. So if we have, let's say, some N resistors connected in series, in general case, we can write that R equivalent is equal to the sum I equal to 1 to from 1 to N Ri. Okay, so now we define how we calculate total electrical resistance of two resistors or resistors connected in series. Let's go for the case when we have resistors connected in parallel. So here we also consider two resistors, but in this case they are connected in parallel, and they are connected to some battery, which has potential difference at its terminals, delta V. So you see, if we show terminals of our battery like these points, let's say A and B, and we can show that points C, D, and E, F, so between all of these points, there are no resistors because these wires don't have any resistance. And that's why we have the same potential difference between points C, D, and E, F as a potential difference between points A and B. So that's why we have delta V here. So let's mark it delta V1. And this is R1, delta V2, R2. But here we can write that delta V1 is equal to delta V2, and this is equal to delta V. So also we need to show some electric current here. But here we split electric current in two channels. So we have I1 and I2. And back, when they come together in this point D, we again have current I. So obviously, if we split charges which move through these wires in two channels, per amount of charges per time interval will be smaller in these parallel channels than before this so-called junction point. And that's why we have, since we don't lose electric charges while they move through wires, they just split into different channels. We can write that I is equal to sum of electric current in the channel 1. This one should be I1 and this one should be I2. So electric current through resistor R1 plus electric current through resistor R2. So keeping this in mind, now let us again ask a question. Is it possible to replace these two resistors connected in parallel with some equivalent single resistor? So then we have again this simple equivalent circuit with R equivalent. Yes, and in order to calculate this equivalent resistor, we should do the following. So here is also some current flowing. So we know that electric current, total electric current, is defined as potential difference divided by resistance. So we can write this for the equivalence for the circuit in the right with equivalent resistor. And the same current will be equal to the sum of these two currents. It will be delta V divided by R1 plus delta V divided by R2. So I put it already here delta V because we have shown here that delta V1 is equal to delta V2 and equal to delta V. So now we can cancel out this delta V, and as a result we get this equation, that equivalent resistor of two resistors connected in parallel like 1 over this equivalent resistor, will be equal to 1 over R1 plus 1 over R2. And in general case, 1 over R equivalent will be equal to the sum from I equal to 1 to N 1 over Ri. And we see that if we compare now connections of capacitors, there is some discrepancy between them. So first of all, if we connect two capacitors in series, we got this equation when we have 1 over C equivalent, it's equal to 1 over C1 plus 1 over C2. So we get smaller equivalent capacitance than the smallest capacitor which is connected in series. However, in case of resistors, R1 and R2, we get the sum. So equivalent resistor is equal to the sum of two resistors. So in case of resistance, we increase resistance, equivalent resistance, by connecting resistors in series. In case of capacitors, we reduce equivalent capacitance by connecting two capacitors in series. And in the contrary, when we consider parallel connection of resistors and capacitors. So this relationship between connections of capacitors and resistors, please keep in mind, because it could be at some point a bit confusing. Okay, so we just will try to introduce now two Kirchhoff's rules, and we'll work with them in details on our next lecture. So Kirchhoff's rules, they are very useful in order to determine electric current and potential differences at different segments of DC electric circuits. Also is valid for AC electric circuits, and we will consider them a bit later. However, there are two key rules. One is so-called junction rule, and it states that at any junction, so when we have one wire and then it splits in two, this point is called junction. So at any junction, the sum of all currents must be zero. So if we have some current which goes to the junction, and then some currents which go from the junction, then the sum of these currents, when we assume that this current which goes to the junction is positive and currents which goes from the junction are negative, should be equal to zero. So in this case, I minus I2 minus I3 is equal to zero. And this junction rule, it's like first Kirchhoff's rule, comes from the law of conservation of electric charge. So that's what we partially discussed previously. Now, the second rule is so-called loop rule. And it states that the sum of potential difference across all elements around any closed circuit loop must be equal to zero. So we can define this as the sum over a closed loop should be, like, of this potential difference should be equal to 0. And this second rule comes from the law of conservation of energy. So what it actually tells us that if electric charge move around a closed circuit, then when charge returns to the starting point, the energy of the charge circuit system must be the same as total energy of this system before electric charge start to move. So in other words, the sum of the increases of in energy as the charge passes through some elements of electric circuit should be equal to the sum of decreases of energy as electric charge moves through other components of electric circuit. So those components of electric circuit which are increase potential energy of charges, these are batteries, like with their electromotive forces, and other components where potential energy of electric charges decreases. These should be some resistors where electric energy is dissipated. So in a closed electric circuit, this change, the total change, should be equal to 0. That's what we considered at the beginning of our lesson when we started from point A, went through all electric circuit, came back to point A again, and our potential at point A was 0. So there was no change in potential when we have a closed loop along the closed electric circuit. So we will discuss this in more details and solve some examples for application of Kirchhoff's rule already at our lecture, next lecture, which will be on Friday. Okay, guys, do you have any questions? And you're welcome. Ask.
No questions. Thank you. Goodbye.
Okay, thank you for attention and have a good evening. See you on Friday.
Thank you.
Bye bye, guys.